afternoon. Let's get started. I'm going to break up Stokes' theorem into two halves. The first half we're doing today, I'm calling them version 1. And the second half, we're going to do them tomorrow, and I'm going to call them version 2. Question 1 is actually numbers 1 to 8, but we've done 1 and 2 earlier, so I'm not doing those again, right? So we are going to be calculating this type of integral, right? This line integral, by turning it into a double integral, which is a surface integral. But actually, we don't do that directly. Stokes' theorem says that this line integral can be rewritten as a surface integral. But this surface integral is itself going to get converted into this double integral. And so what we're going to do is we're going to take a surface integral and convert it into this guy here. So we're basically going to go from there to there. So we've got to get some terminology sorted out here because there's some overlap and confusion in the notation, which got me a little bit yesterday. Can you imagine this green thing being the surface? The curve that they're talking about, the C guy, right? The C here is that red line, and it has an orientation of plus or minus. And the region D is the region that's inside the C. Right. So the double integral of D is the shape inside C. So D is this guy. Obviously, it won't be as ugly as that. It'll probably be a circle, rectangle, or triangle, it's most likely. So D will be a circle, or what's inside the circle, a rectangle, square, what's inside it, or it could be a triangle, which is another possibility. Actually, in this question, it's a triangle. So we are going to find the limits of integration of this area once we figure out what it is. And it's going to be negative p dq dg by dx minus q dg by dy plus r. And g is going to be this fella here. So g is going to be a function of x and y, right? It's going to be a z equals function of x and y. So that's the guys that are going to go here. This guy that's called the curl, we're going to find that guy. But when we get the curl, this guy here is going to be called P, this guy here is going to be called Q, and this guy is going to be called R. Normally, don't we call F P, Q, R? But just for convenience, the curl F is going to be called P, Q, and R. And that's where this bit's going to come from. And since everything's being converted into X's and Y's, then it's a dx and dy. So that's pretty much the whole process. And the one that I kind of started and lost it is this one here. And got my notes because I did it again. So it's going to be a version of 3. Is that 1? That looks a bit wrong. Ah, it is 1. Okay. 1, x plus y, z. That's good. It's the same. And x, y take away z. And in my case, C is basically this plane in the first octant. So we know that there's lots of bits and pieces that we need to get, and then we put them all together, we'll be able to get this integral, this double integral. And the answer to that is what we're looking for. So let's do the curl again. So to get the curl of F, we are going to do the cross product of the gradient with F. So there's going to be an I, going to be a J, and there's going to be a K. The operator for the grad is d by dx, d by dy, and d by dz. And this guy here is going to be, so we have a 1, an x plus yz, and an x, y, take away the square root of z. So the curl of F is going to be so many i's take away so many j's plus so many k's. So far, so good. Right, let's do the cover-up stuff. If you differentiate this guy here with respect to y, you get x, take away y. Differentiate with y, you get x, differentiate with respect to z, you get y. If you move on to the middle one, if you differentiate this guy with respect to x, you get y, take away nothing. If you go to this one, you get 1, take away nothing. So the curl is x take away y, negative y, and there's a 1. And I believe there might or might not be an orientation associated with this one, and I'll figure that out later. Oh, by the way, we had a discussion at the end of, I think it was last lesson, about what made it positive and what made it negative. And I think the conclusion was it's not clear. So you assume that it's positive unless they tell you it's negative. Was that essentially what we decided on, Matthew? Right. Okay, so we're going to assume this is positive unless there's some indication that I haven't bothered to read over that says it's not. So that's good. And I'll put a bubble around it because I want that guy. And I'm going to call this guy P, this guy Q, and this guy R. So that when we do this, that's P, that's Q, that's R, right? P, Q, and R. Now, moving on now, let's use this guy here to figure out what the surface formula is, what the g of x, y is. Now, we're told that it's a plane 5x plus 2y plus z equals 1. And if I rearrange that, you get 1, take away 5x, take away 2y. So here is our g of xy guy. Are you comfortable about how we figured him out? Now, the next piece of the puzzle that we need is we need to know the limits of integration of d. And what that ends up being is we take this surface and we find out how does this surface interact in the first octant. So if you imagine where the first octant is, it's here. And if you take this equation, it crosses the x-axis at 1/5. And if you're wondering how I know that, if you make the other two 0, 5x is 1, so it crosses the x-axis at that value. If you want to know where it crosses the y-axis, you make these two guys 0 and you get 1. I'm making no attempt to do this to scale. And if you do that guy, you find it crosses at 1/2. So essentially, can you imagine this triangle looking pyramid-y shape is the surface, right? Now, who is D? D is this guy on the floor. So you project your surface down to the XY plane. That's how you typically do these questions. So transferring that information over here, I know it crosses the X at 1/5 and it crosses the Y at 1/2. And so the region I'm interested in is that guy. And so the limits of integration are x's go from 0 to 1/5. And I'm going to do my type 1, which is my vertical rectangles. And that tells me that y will go from 0 to whatever the equation of that line is. And I think that's kind of where we got to last time. The equation of this line, well, I need to know its slope, its rise over its run, which is 5/2, and it's negative. So it's negative 5/2 x, and it crosses the y-axis at 1/2. So we now have negative 5/2 x plus 1/2. Are we good so far? I found the curl of f because I need to know it. I found out the equation of the plane, the surface in this case, g of xy. I now have the limits of integration, right? That's the three key pieces of information that I should now tie together here. So we're totally bypassing that and creating this double integral, which is equivalent to that. So the guy that we want is going to be the double integral of, well, yeah, x should go first. From x equals 0 to 1/5. From y equals 0 to this horrible expression. And then it's going to go negative p, okay, we got these guys, negative p, that's this fella, times the derivative with respect to x of this guy. So it's going to go negative p times the derivative of this guy with respect to x, which is -5. Then it's going to be negative q, which is this guy, times the derivative of g with respect to y, and that gets you a -2. And last but not least, you get plus an r, and the r happens to be 1, so you get +1. Are you comfortable about where all the bits, all these bits came from, right? We found them in various places, including these limits of integration. So that's going to be from 0 to 1/5, and that's going to be from 0 to that guy. -5 times that makes it +5, and if you multiply them out, you get 5x, take away 5y. Negative times a negative times a negative gets me -2y plus a 1. That gets me the integral from x equals 0 to x equals 1/5, from y equals 0 to y equals -5/2 x plus a half. 5x take away 7y plus 1 dy dx. And that's kind of where I'm going to stop on that one, right? I think the back is broken. This particular question didn't have a z in it. You know, this plus r was just +1. Can we pretend it said plus z or plus z squared? If that had happened, if it had said plus z squared or something, wouldn't the z be replaced by a 1 minus 5x minus 2y? So that's how you would get rid of any z's that happen to be left over in this expression, right? So if you found any z's, replace them with 1 minus 5x minus 2y, and you're done. Now, I haven't even finished that question, but it probably would take 20 minutes to do. So we're talking not a lot per minute, right? One last chance. Are we good with this question? Anything that's not sure, because I'm moving on to the next one. Okay. Jump right into 4. I'm hoping to get 3 questions, if I'm really lucky, at least the start of the 4th one in the short time that we have. So here goes. We're being asked to find that guy. This fella is xy, yz, zx. The z that we're talking about is 1 take away x squared, take away y squared, and again it's in the first octant. Right, I need to know the curl of f, so I might as well do them in the same order I did last time. So that's going to be an I, a j, and a k. This fella. And a xy, a yz, and a zx. So we're going to have so many i's, take away so many j's, plus so many k's. If you differentiate this with respect to y, you get nothing, take away a y. If you do the middle one, you get a z, take away nothing. And if you do the last one, you get a nothing, take away an x. And, oh, that's cool. There's a kind of symmetry in that answer, isn't there? And that's going to be the P that we're going to use. That's going to be the Q, and that's going to be the R. So I'll put a bubble around that so I can find it when I need to get it again. Now I need to know three things, right? I need to know the curl. I need to know G of xy. Actually, that's G of xy, right? That's the equation of the surface. So I didn't need to do anything. I just needed to, you know, recognize that that's what it was. Now, we need to figure out what does that thing look like when you project it down to the floor and you keep it inside the first octant. So the first octant is positive x and positive y's. If you put that on the floor, right, if you project, oh, excuse me. Oh, I apologize. We're back, so hopefully you're still here with me. We have this fella here, and what we're trying to do is, what does this surface look like when you project it onto the XY plane and you restrict yourself to the first octant? So if you put a 0 here, and you do a quick rearrangement, oh, that's what you get. That's D. Which means how am I going to deal with limits of integration? And in general, how am I going to deal with all these x's and y's? We've got a quarter of a circle. How are we going to deal with it? Come on, guys, I'm getting old here.
So we can end up using polar.
Yeah, we're going to have to go polar. So, as far as polar is concerned, it's going to go from 0 to 1. What's the range of theta going to be for this guy?
5/2.
Right, great. Yeah. Now, I could do this two ways. I think I'm going to stick to the x's and y's first, and then at the end make everything polar, right? Just to make my life easier. Because I don't think there's any great advantage to turning a lot of these things into r sine thetas and r cos thetas. It's just too early on, right? So we have got our limits of integration. That's d. So we can now put the package together and use this guy. So it's going to be a double integral. And the guys that we're going to do are theta equals 0 to pi upon 2. And r is going to go from 0 to 1. I'm going to keep all of this stuff here with x's and y's, but I am going to do a dr d theta at the end. So what are we going to do? We're going to do negative p. So that's p. So negative of p times dg by dx. So if you take this guy and differentiate it with respect to x, you get negative 2x. That's the first one. Then you go negative q, which is that guy. And you differentiate that with g with dg by dy, which gives you a negative 2y. And then you add an r, and r is add a negative x. So I'm not going to put the limits on that, it just takes too long. This times this times this gets me positive 2xy. That's a 2, but that's a z. So that's, well, there's 3 of them, so it's negative. Negative 2 yz's. Take away an x, check that out. 2xy, 2yz, okay. Or dr d theta. So it's going to be negative 2 r cos theta or sine theta. Negative 2 r sine theta. What am I going to do about the z? What's that z going to be equal to in terms of x's and y's?
Wouldn't it be like 1 minus r squared?
Yeah.
Yeah, okay.
1 minus r squared. Run short room, take away an x, which is this fella, all times r dr d theta. So we're going to have from 0 to pi upon 2, from 0 to 1, negative 2 r, I'll bring in the r each time, so that's going to be r cubed sine theta cosine theta. Oh God in himmel, this is just ugly. Putting in r here, so what am I going to get? Negative 2r squared sine theta, a plus 2r cubed sine theta, a minus r squared cos theta d theta. I don't see anything particularly obviously connected here, but aren't all the 4 pieces doable? I mean, if you just look at each one in turn, couldn't you do that one, right, by variable separable? Couldn't you do that one by a variable separable? Couldn't you do this one by a variable separable? And lastly, that one. So I think I can put a dot, dot, dot on that. It's just going to be 4 separate integrals, all using the same range. And each one of them, that one, and that one at least are easy to do. And this one here, you could probably do with a U sub if you wanted. Matthew, question.
Wouldn't the third one be r to the fourth?
This one here might well be.
Yeah. Thank you.
We good? Right. That's as far as I want to go with 4, because each one has its own little idiosyncrasies. And I think it's better to show you a little bit of many than everything of just 2. How far do I need to go for this type of question? I think 8. What's the last one? Don't know. So I got a 5, I got a 6, I got a 7. I do have an 8. Okay, so 5, 6, 7, 8. Let's just move on. I'll set up most of 5. So we have this thing, as always. In this question, the vector field is 4y x, z, x plus y. And C, it's a little bit trickier now. C is the intersection of the plane z equals y plus 6 and the cylinder x squared plus y squared equals 1. Now, if I did the cylinder and you did it in GeoBra, can you trust me that it would look like that? I mean, it'd be an infinite one, but it would look like that. And if you did a plane, can you imagine the plane would just be coming in diagonally, cutting the shape and then continuing? But where they meet, I know it looks more like a circle, but it's probably going to meet at an angle. Won't it be an ellipse? But won't that ellipse, because it's inside the cylinder, actually just be a circle? Won't that be what the surface looks like? So the surface is this elliptical thing, but if you project it onto the floor, it ends up being a circle, which means it's just that guy. So that was a long-winded way to say, I know who D is, even although it doesn't look particularly obvious what D is in that question. Are you okay with how I figured out what D is? Yes? No? Are we good?
We're good.
We're good, thanks. Somebody said we're good. That helps a little bit. Right, now, I have all the bits and pieces that we know we need to get, and so I'm going to just be consistent. I'm going to find the curl of F. And there's an I, there's a J, and there's a K. And then you have the operator. And then you have a 4y, an xz, and an x plus y. Oh, we'll come back to that again in a minute, but I'm going to have to go polar. So we're going to have so many i's, take away so many j's, plus so many k's. So if you cover this guy up, you get 1, take away an x. If you do the middle one, you get 1, take away nothing. If you do the last one, you get z, take away 4. So the curl ends up being 1 minus x, negative 1, z minus 4. And that guy's going to be my P, that guy's going to be my Q, and that guy's going to be my R. So that's one of the 3 things I need. Now, second thing I need is the equation of the plane. And the equation of the plane is actually just y plus 6. And you might say, well, it's cutting through a cylinder, doesn't have any effect. Well, not really. All the points on that cut, which is basically this surface, this diagonal surface, all lie on that plane. So there's your g of xy, which is y plus 6. Now, I need to know the region, the limits of integration. Since this is a full circle, and I'm making sure it's not anything else, right? Since it's a full circle, we are going to be talking about polar. And it's a unit circle. So I'm going to do the 1 and I'm going to do the 2 pi. Are we comfortable with that? And that means, of course, doesn't it mean, just like the previous question, aren't we going to have to turn everybody into r's and thetas at the end? But right now, I'm just going to keep everything, as many things as x's and y's as I need to. So the original question, which is this, that, is going to be the double integral from theta equals 0 to 2 pi, and from r equals 0 to r equals 1. And I'm using this guy over here. So it's going to be, here goes, negative p. Right, so you stick in negative, a 1 minus x, and then you differentiate this guy with respect to x, which gets you a 0. That's good. Then you take negative this guy, which is what, negative 1. And you differentiate this guy with respect to y, you get times 1. And then you add r, and r is this guy, z take away 4. And since we are in polar, I'll at least call that r dr d theta. So it's going to be from theta to 2 pi, from 0 to 1. That guy is negative 1. That's nothing. That's just nothing. Okay. That guy is 1. That guy is z. That guy is take away 4. So 1 and that guy. Z gets replaced. This guy. That's essentially who Z is. So it gets replaced by y plus 6. So what do I get? I get y plus 6. Add 1 is 7. Eventually you get y plus 3. So what I did is I had 1 here. I had y plus 6, and I had a takeaway 4, and the whole thing gave me that. Almost done. 0 to 2 pi, 0 to 1. That guy becomes r sine theta times another r, and this guy here becomes 3r dr d theta. Are you comfortable that the back is broken now? Would you agree you could just finish that off in the usual way? If they had added in the first quadrant, wouldn't my whole circle just be 0 to pi upon 2, and pretty much everything else the same? So this stuff here does not get affected by whether it's the first quadrant, the second octant, or things like that. That doesn't get affected by it. These do, because the limits of integration depend on what region your shape is in. And if you're wondering who is the g of xy, if there's a z equals something, whatever that something is your g of xy. So in that case here, it was like z equals 1 plus y, right? That was the plane. Are the more of these I'm doing, the cleaner the process is getting in your brain, right? And it's really, you know, I wish we had 20 hours to do all of these, because then we could do them till you're sick of them but that means if you ever saw one, you'd know what to do, right? There's still a little bit of, you know, thought process going on, but here's number 6 then. Same guy, same question. Right, they want us to find that line integral. The vector field this time is negative 1x squared. This guy is an x squared, y squared, and this is an e to the xy. And C, oh, isn't that nice? They told us who C is. They told us it is a circle radius 4. Oh, they gave you that one for free then. Of course, since it's a circle, and it's the whole circle, that means D is that region. Okay, I can live with that. And I need to find the curl of F. Actually, this might not be the last question. I might stop this one a little bit early because I want to show you one more that I've just noticed. I want to at least give you a head start on. And we have a negative yx squared. We have an xy squared. And for some reason, we have an e to the xy. I hope that doesn't actually join in. So many i's, take away so many j's, plus so many k's. Oh, shooting space, it is going to be in the question. Okay, so if you differentiate this guy, you're going to get x e to the xy, take away nothing. If you do this guy, you're going to get y e to the xy, take away nothing. And if you do this guy, you're going to get y squared, take away, which means you add an x squared. So we have this term, and this term, and that's the curl. And I guess all we're short of now is, who's our G? C is a circle. So where's my surface? Where's my surface? In case I miss something. Use Stokes theorem. Yep, blah, blah. Counterclockwise. Okay, blah, blah. Function, yep. C is a circle in XY plane. 4 centers in the origin. So that's my circle. So who's my Z? Who is my Z? Oh, shoot. I didn't swear there. Z is 0. I mean, if you tell me that's C, aren't you also telling me that that's my surface? And my surface is on the floor. The only way my surface could be on the floor is if that is 0. Oh. What a downright sneaky question. I didn't know that until I did it. Okay, we got all the pieces. And so we'll use our integral, our formula, this one here. And it's going to look like the integral r equals 0 to, was it 4? Theta equals 0 to 2 pi. He's P, he's Q, he's R. So you are going to be doing P, which is negative P, so it's negative x e to the xy times the derivative of that with respect to x is 0. Oh, okay. Take away y e to the xy times the derivative of that, which is 0. okay, plus r. And r is plus x squared plus y squared. R dr d theta. Oh, that is so elegant. Oh, the person who figured that out was cool. Because these are zero, they don't matter. Aren't you just left with an x squared plus y squared? Oh, which is r squared. And that makes you an r cubed dr d theta. What a pretty looking answer. And the only thing that caught me was there wasn't anything in the description like z equals x plus y, like some kind of plane cutting through. But if you tell me that C is on the floor and it's that, isn't that the surface z equals 0 meeting up with the cylinder? So that's how I figured out it was z equals 0. And now I do have 5 minutes, that's all, to show you the last puzzle one. Let me stop this fella and show you the question. That's the last one. 8 is the last one of this type. So you always expect they keep the best till last kind of thing. So it's the classic find the line integral. Clockwise or counterclockwise just means it's positive. There's the answer, which is annoying. Let's do the easy bit. Would you agree that f is kind of, it is what it is, so getting the curl is usual. They tell you C is this equation. So C is this guy. Now, that is actually an ellipse in 3D space. Great. It's a diagonal ellipse. Now, I want you to imagine that you were above it, looking downwards onto the XY plane. If you were doing that, won't the Z be 0? Right? And the Z is 0, that's what the curve would look like. Who is x equal cosine t and y equals sine t? What does that look like on the xy plane? Because that's the region D. What does x equal r cos t and y equals sine t look like on the floor, on the xy plane?
Is it a unit circle?
It's a unit circle. So isn't D just a very well hidden unit circle? Are you with me? Okay. Now, this particular one, let's just leave it at that. That's not the way I would do it, but that's fine. That's another reason I don't like solutions. If you take the guy the way it is, isn't it reasonably obvious that you're going to use polar, right? And I know these are ugly. I'm just assuming that the curl is nice, or at least once you've converted everybody into X's and Y's and then convert them into T's, I'm assuming that everything nice comes out. Now, based on the fact that the answer is pi upon 2, and that when you do it as polar, this is what you get. Oh, there's a few zeros and ones floating around, right? So it does come out nice, right? So it isn't as bad as I thought. So you're basically going to get 0 and 0 out the first two terms, and then the guy at the end is the only one that's going to live, and then you turn it into polar, and that's what all this stuff here is, just the polar part. But that there is your minus P dg minus q dq, and that fella there is your Z. And where is our Z? Yeah. Okay, we are good to go. Last